Hello, class. We're going to go over some parts of Chapter 8 today, and then we'll go through the rest of Chapter 8 whenever we meet in class again, and we'll also practice building some of the structures that are in 8.2 and their angles, that sort of thing, in person. So a few of the things I wanted to highlight from 8.1. First of all, that the composition and the arrangement of matter determine its chemical and physical characteristics, right? So how it's all put together determine a lot of the characteristics that we know of, the chemical and physical characteristics. The Lewis structure has done a really good job of showing us basically a two-dimensional figure, right? However, in real life, these molecules and structures are three-dimensional, right? And there's a lot more that take place. The Lewis structure, the Lewis structure is more of a model. So remember, models and theories can always be altered, right? So there's always things that we're going to learn that's going to adjust things a little bit, right? So the Lewis structure is fantastic until you reach chapter 8.1, and then you realize that, oh, there's all these other theories that we can use, but it gives you a good understanding of the number of bonds and that sort of thing. So let's see here. Valence bond theory. So let me pull out some of my notes here. So the quantum mechanical theories that we're going to learn about are the valence bond theory and the molecular orbital theory, right? So quantum mechanical theory sounds really scary, but it's not. It's more just a complete description of the bonds and their shape for a 3D structure versus the 2D structure of a Lewis structure, So quantum mechanical theory doesn't have to be scary. Valence bond theory, right, which is what we were reading about here in this first section. This right here tells you more so in summary why molecules have certain shapes, right? So it is going to focus on the localization of these electron locations, okay? A good definition is, or a good thing to remember, is that covalent bonds of two atoms with opposite spins, right? So a covalent bond of two atoms, right? They've got these electrons that have opposite spins, and they're going to occupy those valence orbital regions that overlap between these bonded atoms. Okay, what do I mean by valence orbital regions? So remember, we've got orbitals, right? We've got the s orbital, the p orbitals, the d and the f orbitals. So actually, real quick, let's review that. So the s is a single orbital, right? And each orbital can hold 2 electrons, right? So the p orbital, remember, the p level has 3 orbitals, and it can hold 6 electrons. And the d has 5 orbitals, it can hold 10 electrons. And the f, do you guys remember, has 7 orbitals, and it holds 14 electrons. Okay, so when I talk about these valence orbitals, it's the outer shell that has those valence electrons in it, right? So whenever they overlap during this covalent bond, we're going to look at where those electrons are going to occupy that region. That overlapping space, right, whenever they overlap, so let's say we've got 2 s orbitals, right, it's a single orbital, the overlapping space, and then the electrons in that space in between are going to be really readily available then to both nuclei of both of those atoms, okay? Let's see. And both of those atoms are going to have use of those shared electrons, right? So one of the things I would like for you guys to do is we're going to put together a T-chart for the different bonds, for the sigma and the pi bonds. This is going to help, I think, on your test whenever you guys are kind of looking at your notes for the bonds, the different bonds. So the sigma bonds and the pi bonds, we're going to talk about which orbitals are involved, and the way that they align is going to give us either a sigma or a pi bond, okay? So the sigma bond, I'm going to summarize. You guys already read all this stuff, and you guys already answered questions on all this. So I'm going to summarize here and just explain anything that might be confusing. Okay, so the sigma bond. So one thing to remember here is that the orbitals overlap along the bond axis that connects the two nuclei, okay? So let's write this out and then we'll talk about it. Orbitals overlap along bond axis, thus allowing I don't know how to spell nuclei, guys. Nuclei to connect. Okay, so if you can remember, sigma bonds, right? Overlap along the bond axis, allowing the two nuclei to connect. Okay, and this will make more sense as we go, right? So if we have two s orbitals, right, and they're going to overlap along this bond axis right here, okay? And then the nuclei, which are inside, it's going to allow those to connect, okay? All right. The next thing to remember for the sigma bonds is that they have an end-to-end overlap. Right? So if we look at a single p orbital, remember a p orbital is shaped like a peanut, right? They're going to end to end, they're going to connect right here, right? On their ends. The picture that they showed you in your book was good, but it was a little confusing, right? So they're gonna connect end to end. They're gonna have this end to end overlap. That's another key part, okay? So this is gonna be that bond axis. Axis, not access. Let's see. There is a high, that's what I'm gonna use for high, electron concentration along the bond axis. Okay, so there's going to be this higher concentration of electrons where it meets, right, along this bond axis right there. They're going to be shared. Again, they're going to connect those two nuclei. And let's say you've got one electron out here, right? And then you've got another electron out here. You've got two here, right? So you've got more that are in that, there's a higher concentration along that bond, okay? What is that gonna do? That's gonna have a higher electronegativity, right? That's gonna have this higher, electronegativity wasn't the right word. It's gonna have a higher electrostatic force, right? Because it's going to have this, this negative pull, right? So that's where it's going to play a part into 8.2, where it's talking about the structure and the angles of our bonds. Okay, so let's see what else here. Okay, one interesting thing with the sigma bond too is it can cross orbitals to form bonds, right? So example, we can have an s orbital and a p orbital, and then here's our bond axis, right? It can cross orbitals. What I mean by cross orbitals is we have different orbitals. We've got an s orbital here and a p orbital here to form bonds, okay? This is a sigma bond. All right, another thing of note about the sigma bond is it is the strongest because of the highest electron probability on the bond axis, okay? So this bond, the sigma bond, is strongest. Because of the highest electron probability along the axis. Okay, and remember, electrons are mobile, right? So they're going to be moving around they're going to be moving around those orbitals, but whenever you look at where they are, it's actually looking at the probability of where the electrons are going to be. So the probability of them being along these bond axes is high, okay? So the sigma bond is the strongest because of that highest electron probability along the bond axis, okay? So, all right, let's look at pi bonds. Let's see here. Okay, so we're looking at double and triple bonds. They form when greater than 1 orbitals from the p sublevel overlap. Okay, so remember, p has 3 orbitals, right? And so when more than one of those orbitals are going to overlap, that's when we have the double and triple bonds, okay? So something more like this, right? That's the P for peanut. So whenever we start to have a bond here and a bond here, right, between one of this right here is one orbital, that's another orbital of 2 different atoms, right? So we're going to start having these double and triple bonds. Okay, and these are going to be the pi bonds. The pi bonds are let's see here, I'm going to just underline the highlighted parts here. Greater than 1 orbitals from the p level overlap. These right here, the pi bonds, have a side-to-side overlap. Okay, side-to-side overlap. Right, versus the sigma bonds have an end-to-end overlap, right, like right there. Okay. These bonds are actually weaker because the electrons are over a greater volume of space, not just along, there's not a single bond axis that they're going to be at. There's this greater amount of space that these electrons have to travel and go around, so these bonds are weaker. And I'm talking about the individual pi bonds, okay? Weaker because the electrons are over a greater volume of space, not just along the bond axis. Okay, guys, I'm gonna look real quick, make sure that I am still recording. Let's see here. Sorry guys, give me just a second. Just want to make sure that I'm not moving around here and you guys can still see everything that I'm doing. Sorry, I broke my stand. Okay, I think we're still good, guys. Okay, so let's see here. One thing of note, this is not on the pie chart, this is just separate. Sigma and pi bonds usually occur together, okay? Sigma and pi bonds occur together. Okay? All right, so that's the summary of sigma and pi bonds. The next thing we're gonna look at is molecular resonance. So whenever, and I think we briefly talked about this in class, but with molecular resonance, it's basically looking at a structure, a molecule, and saying, does this double bond, can it go here or here or here? Because you've got resonance, right? You've got, let's say there's 3 oxygens or 2 oxygens around a central atom, and you know that there's a double bond, right? It can go to the one on top right, top left, or the bottom, you know, like which one does it go on, right? So molecular resonance, they've done some research, and basically it shows that it's not like it hops, right? I'm going to go to this oxygen, then this oxygen, then this oxygen. But basically almost like the bonded energy is shared, right? So it's almost like they have a portion. So they each have one bond, and then they all have a portion of that double bond, right? So for example, one of the ones they did in the book was, let's look here. So sulfur, and then there is oxygen, sulfur dioxide, I think is what this is called. So, right, if this oxygen is double bonds, it's going to only have these 2 unpaired set of electrons. This oxygen is a single bond, and it's going to have these 3 pairs of unpaired electrons, right? And sulfur is going to have its 2. But whenever they researched it, they show that these 2 bonds right here have the exact same strength, right? And the same length. So it's clear that this double bond isn't just jumping over here, and then these unpaired electrons are jumping over here. You know, it's not jumping around. But basically what they said is that with molecular resonance, it's almost like you have a partial bond, right? So you might see like a dotted line to show it's almost like they each are sharing that last bond, so it's a half a bond. And then the central atom will still have the electrons, the unpaired electrons visible, but the ones that have the resonance of the bond, you will not see the unbonded electrons, and it's because you don't know which one's going to have the 6 versus the 4. You know, that right there is going to vary. And then in reality, those electrons are mobile, and so they're actually going to be equally spending time on both of those, right? So anyways, that's molecular resonance in a nutshell. Let's see, let me know if you have any questions with that, because really it's not terribly confusing. There was a few other examples they gave in the book, and it's just it's not one way or the other. Like if they talk about actually just scratch that. So just always remember though that you're going to have molecular resonance if there is the same atoms that are connected to a central atom, right? If I have I don't even know if this is anything, but let's say I have a carbon, and then I have I don't know, an oxygen and a hydroxide ion, and another oxygen and another oxygen. Again, guys, don't quote me on this. I have no clue if that's even anything. This hydroxide ion, this is not going to experience the resonance, right? Only these 3. So they have to be the same outer atoms. experiencing resonance. Okay, because you get into some crazy molecules later on. Okay, so we're going to move on to the next section. So a quick review about the octet rule, right? The octet rule is where different elements will lose or gain electrons in order to have that full 8 valence outer shell, right? They want to be those noble gases, okay? So, and some exceptions to that are the D and the F block elements, right? So remember on, let me pull this out here real quick, the D and the F block, which are the transition and the inner transition metals, right? Remember we have S, P, D, and F. So the D and the F, okay, they do not apply, the octet rule does not apply to them, nor does it apply to the first 4 to 5 elements, right? Like hydrogen, lithium, beryllium, and helium and boron. It really doesn't apply to those because they have, remember this, like boron has 3 valence electrons, and it's going to be happy getting rid of those 3. So it's going to be like helium, right? Because you look at the one above it and the period above it, and just having its outer shell be 2, right? So remember, if there's 4 or less electrons, then that element is going to be happy to get rid of those electrons to expose its undershell, right? Its undershell that's already full of electrons. And so with beryllium over here, right? Beryllium has 2 valence electrons, so it has 2 in that outer shell. It really is okay just getting rid of those 2, so then it would be like helium, right? Helium's valence and very happy S orbital only has 2, right? Because all the other ones want 8, right? So again, that's just a quick review that the D and the F block elements, which are the transition and the inner transition metals, and the first 4 to 5 elements are happy just being helium. Just being helium, right? They've got 2 valence electrons, they're happy being helium. They don't need the 8, the special 8. All right, so let's see here. Definition of free radicals. A lot of us will hear about free radicals in, gosh, you hear about it a lot, I feel like, in cancer, right? So carcinogens, and you also hear about it with like skincare, different foods that we eat, and just the environment that we live in, right? Breathing in different free radicals. But anyways, what is a free radical, right? So it talks about that. So it's actually a substance with unpaired electrons, right? So it has an odd number of electrons, so it's going to have an unpaired electron somewhere. And these are going to be really reactive, right? They're going to really want to react with other things in the atmosphere, right? Or other living organisms. So they're going to be really reactive, and they can cause damage to living organisms, okay? That's why you'll hear a lot about those, like I said, in the world of carcinogens, cancer-causing agents. So anyway, so again, free radicals are substances with an odd number of electrons. They have an unpaired electron, and those are called free radicals, okay? So let me see what example they gave you here, and I can show that to you. They showed you nitrogen dioxide on page 178. So if you look there, it's also, there's some molecular resonance there. But nitrogen is with oxygen, and it only has 2, 4, 6, 7. It only has 7 electrons, valence electrons, right? This one right here is an unpaired electron. Remember, they love to be paired. So again, it's going to be a pretty reactive element, and it can cause damage, especially to living organisms, okay? So let's see, what else did I want to touch on? Oh, a few definitions too that they wanted you to be aware of are electron deficiency. That sounds pretty standard, right? Electron deficiency is some elements like boron, they're content with less than 4 pairs of electrons, right? Boron just is. So instead of having 8 in its outer shell, he is a happy guy just having 6 or just having 7, okay? So the example that they gave you is on page 179. So just know that that is the definition of electron deficiency, when you have elements that are content and happy with less than 4 pairs, less than 8 valence electrons in that outer shell, okay? They're not fulfilling that octet rule, okay? Wouldn't it be great if everything just abided by rules and there were not exceptions? You know, we learn about something in one chapter and then the next chapter it goes and it's like, well, but then there's all these exceptions. So it makes it a lot more difficult. All right, and then another definition was the hypervalent molecules. Again, if you look at the prefix there, hyper just means more, right? Hypervalent molecules. So the central element is going to be happy and it can have more than 8 valence electrons, right? So remember the octet rule is 8 and it's going to be happy with more. Let's see, these are only found in periods 3 and above, right? So again, here's period 3. So 3 and above. So it's only going to be found with those. Okay. Let's see. They also call that an expanded octet. So just remember that. You can look at the example if you want on page 179. And that has sulfur bonding with 1,000,000 fluorines. Actually, it's just 6, but it looks like 1,000,000 fluorines. So he has 12 in his outer shell, right? All right, one more thing I wanted to touch base on. Let me make sure my phone is not gonna die. Actually, guys, I'm gonna plug my phone in real quick, so give me just a second. Hey, Lucy, would you be able to run and grab me a phone charger? Okay, thanks. Okay, so the last thing I want to touch on is molecular orbital theory. Let's see here. Well, yeah, because we're already running. I'm already talking a lot here. So molecular orbital theory. Let's see here. So basically with molecular orbital theory, it's really, honestly, it's a little confusing, isn't it? I think it is. Just know that the electrons in the bonding orbitals, they help to stabilize a molecule, right? So electrons in bond, I think that was on our last test actually. So the bond becomes more stable. Those molecules are more stable. So bonded orbitals stabilize a molecule. Okay, bonded orbitals stabilize a molecule. And with molecular orbital theory, it's used to predict whether a bond will form basically between 2 atoms or not. Is it going to form or is it not going to form? So atomic orbitals of a molecule's atoms are replaced by totally new orbitals when a molecule does form. Thanks, Lucy. Right? So what does that mean? So you learned probably as you went on a little bit that they're going to form new orbitals, right? And they're going to be called basically a combination. We'll look at some of those. But just know that the atomic orbitals of a molecule's atoms, they're replaced by totally new orbitals and they're named a little differently as well, right? And the unpaired electrons in those orbitals will predict whether or not what bonds will actually form, right? They're going to say, okay, so here's my electrons. Will this bond actually happen, right? Let's see here. Okay, let me plug my phone in real quick here. And then we'll look at that. We're at 30 minutes, guys. My goal is to not go more than 40 for you. Sorry, give me just a minute, guys, as I look for an outlet here. Hey, Lucy, would you also be able to grab me an extension cord somewhere? Yeah. Okay, thanks. Okay, so what do I mean by a rename? You guys probably saw this already whenever you're doing your homework. But let's see here. You know, I think they touch on that a little bit later, orbital hybridization. Yeah, we'll talk about that with orbital hybridization, but just know that molecular orbital theory goes hand in hand with orbital hybridization that you learned about in 8.2, because again, it's these atoms that are totally making new orbitals, right? So this is different than the